slide that I was like, last day before the holidays, to the point that at 5 o'clock, that's it. UCL is officially closed. So thank you so much for being here. You know, I felt like, oh my God, you know, so I'm going to be giving a very short seminar.
At 5 o'clock.
No, exactly. It will be short. It will be short and sweet. I hope very straightforward. So this is work. So the reason why we cannot be uploaded straight away is because this is work that Mateo Neira just finished for his PhD and hasn't been able to get around. He had his viva a few weeks ago and hasn't been able to upload it, you know, to have it ready for in the archives and things. So you know, like, we welcome as much feedback as possible, you know, before uploading it. So that's why. But I hope that, you know, in a couple of weeks you will be there, so to speak. So thank you very much again. So the problem that I'm going to be talking about, you know, maybe I should have oriented more into this. What's going on? Doesn't want to work. Okay, so the problem I'm going to be talking about today, it's about segregation. Apologies for this super busy slide. So if you think about segregation, it's a problem that people have been looking at for, you know, over a century now. You know, actually the Gini coefficient is from 1912. It's a really, really old type of problem, but it's a problem that hasn't been looked at that wasn't looked at in a kind of consistent and systematic way until the 80s with Massey and Denton that identified 5 different types of dimensions. So when you think about the Gini coefficient, or you think about distributions, normally you think about inequality or segregation and these sort of things with respect to how many things you have on one side and the other one. And the spatial aspect is not always put into place. So when you think about the spatial aspect, you have something that relates to evenness. Something also important is that in the 80s, Massey and Denton only considered 2 groups when they were thinking about this. So they were thinking, okay, so when we're measuring segregation, you know, you have this issue of evenness. So how is the population distributed over the whole space? Exposure. So what is the probability of interaction between the different groups? Concentration. So are people really located in a specific place? Centralization. Does it have to do with a specific area of the city? And clustering. Reardon then in the 2000s kind of expanded this work. So we're talking about geography, we're talking about social sciences, this type of things. It says 2002 and here 2004. Not sure what's going on. Anyway, so he expanded the work to multiple groups, so including not only 2 groups, but when you have more. So then you can start to think about this idea of thinking about different distributions of the groups and especially. And then he considered, okay, so actually, if you think about centralization and clustering, there might be these 2 things. So from 5 dimensions, thinking about only 4 of these dimensions. But when you look around segregation, most of the time people only think about evenness and exposure. And most importantly, when you think about back in the day, when people were considering segregation, it was from the perspective of the household level. So at the household level, how do people live in a city? Do they live here or they live there, right? Not with respect to the more modern types of considerations of, you know, like exposure, right? So you also go around the city, as it's not only with respect to where you are, but also, you know, what is called experience segregation, where when you go to work, you also encounter people from different places. And of course, Esteban Moro is one of the main persons working in this type of space. So moving forward in time, in 2018, Philip Chodro produced this very nice paper in PNS that considered mutual information. So one of the main issues when you think about segregation is the scale. The scale and the issue of where the data is concentrated and on which scale you are looking at the problem. So considering mutual information, you kind of avoid this issue of the scale. And this was very much like the starting point for the work that Mateo producing here. So I very much recommend you this paper to look at if you want to to see more about that. So what is the framework? So Mateo is very much interested in spatial inequality. So when you think about spatial inequality, most of the time you might think about the accessibilities and opportunities to jobs, right? So where do you live and where can you work according to where do you live? And of course, this cannot be separated from the transport infrastructure. How you have access to these sort of opportunities, not only how the opportunities are distributed in space, but how you can enhance that with transport infrastructure. But also, who are you really meeting? This idea of the experience segregation is very important, because when you have mixing in the space, then you see that your reality goes beyond what you have locally. Yes, so you're mixed with more people, and this opportunity of encounters really brings a lot into what would be spatial inequality. And so thinking about that, it's which scale are you talking about, right? So when we think about the neighborhood level, is it at school level, who am I encountering, and all of these sort of things? What are my opportunities? Okay, so job, I go more into the city level, but the sort of jobs that you're going to have here and how things are going to be distributed very much relate to the region, right? Then you have all these industrial strategies that are related at the regional level, not at the city level, even though they end up being input at the city level. If you think about the type of strategies that the government is going to bring are going to be at the regional level, and how all of this relates to the country level versus everything is in time. And so thinking about spatial inequality, thinking about all these issues of segregation, which scale do you select? Yes, where are you going to put your intervention in order to change the status of each of those different scales? So that's more or less where Mateo was coming from. And so he said, okay, when you think about all this idea of segregation and you're trying to bring the scales, what I really want to be able to measure is not only whether the places are segregated, but also whether they are disconnected at the same time. So segregated and disconnected at the same time. And so the socioeconomic segregation will be in relation to how the areas are connected between themselves. So overall, the question he wanted to answer is this one, right? So how much information about the population do we gain from knowing the area in which they reside and its connectivity to the wider region? Okay, so if you know something about where the people come from, do you know anything about the status of the segregation, basically? So the relationship between these two things, and this is where the mutual information comes into place. So this is the framework. Should I take off the camera? Yes. No, but because I moved away.
Yeah, this is perfect.
Yeah.
Sorry.
With Palenque in the background. Okay. So how much information about an individual's group class do I gain by knowing the subregion where they reside? So basically, if I say I have this individual and I take it from here, you know, how much would I know to which social class it will relate to? And this is where the mutual information comes into play. So you can imagine that if you have something in this way, you have mixing. Well, you have different types of groups in each of these squares, so you can represent it by each of these different balls. Then you can group them according to this separated into two groups, right? So you will have the tree in which you have each of the groups that belong to each of these different ones, and then they are overall part of the same group. And so for each of these balls, you can know the entropy of the system. So more or less, the entropy will tell you more or less how more mixing there is in that. And so if you go one level up, how much are you gaining or are you missing with respect to the information of this individual? So in order to be able to answer this type of questions, you know, so what Matteo decided to do is first to define the scales of connectivity by identifying the different regions and subregions using, of course, the ones that know me, the percolation process. So trying to identify this idea of nesting within your system. Yes. So which are the different subregions that you will get only via the connectivity of the system. So more or less that brings into perspective transport and how easy it is to get from one place to another. And then once you have that, then you have this nesting bit, which is the hierarchical tree. So any kind of hierarchical clustering will give rise to your hierarchical tree. And then for each of those ones, you compute how much do you have from each of the groups. Okay, so this information that will come from the census, more or less to see how you're going to end up distributing the different populations into the different groups. So then you can measure the loss of diversity, so basically the information in the population groups when the regions are split into subregions, okay? And this is done using the Jensen-Shannon divergence for each parent node. Yes, so it's more or less following these type of things, okay? So you have the entropy, and then you measure the Shannon divergence using from the mother cluster, how much, you are losing knowing what's going on with the other children. Okay, so the hierarchies in the system. So thinking about so why the hierarchies in the system? So this goes back to this idea of crystallar central place theory. So it's something that is not new, thinking about an urban system in terms of different hierarchies, but hierarchies with respect to the type of activities, the type of functions that take place. So not only when you divide the space and you think about regions and you think about cities, you think about London, and London is unique in the type of functions that it has. Another city will have specifically, like the banking system that London has. So it will be a central node with specific type of functions. So back in the day, since 100 years ago, almost, Crystallar proposed this with a toy model in which everything was evenly distributed, perfect competition, and all that. But the whole idea was that the different centers and the different urban systems will have different types of attractions and different type of flows because of the type of functions also that were going on in the space. Okay, so if you don't know the type of functions that go on in the space, just by looking at the flows, you more or less can predict, the importance of those places. So how these things are going to be connected very much tells you that they're places that are more attractive than others without even knowing what sort of functions are in the space. So the way our systems are structured go back to this idea of having a hierarchy, okay? So this is why the importance of thinking about these systems in terms of hierarchies. If you have the flows, and I think this is something that I presented at your birthday celebration that Valentina did. So if you have the flows, then you can know exactly how things are used. But if you don't have the flows, you can more or less take the structure of the space as a proxy of how you would recover these types of hierarchies. So nodes that have more connectivity will in principle be more important than nodes that have less connectivity. Whether the space is used in this way or not, of course, that's something to question. Why is it that this node that has so much connectivity doesn't attract as much flow, right? So maybe because in the past it did have an importance that then it's you have the leftover of that importance. Okay, so I'm repeating again this sort of thing that I said. These are this is the road network. So you get OpenStreetMap, and from OpenStreetMap you use a package that Joe Goin developed, OSMNX, from which you can extract the road network straight away. So from any city in the world, I'm saying this to this group because I'm not sure whether this group is familiar with this and might be useful. So it's just like in Python, in R, whatever, you go into this package OSMNX, and you're able to recreate a network from any street network in the world. Of course, OpenStreetMap will be more completed in places like in developed places where people input more things than in other ones. And I don't know whether you know that actually OpenStreetMap was created at CASA. The person that created OpenStreetMap came from CASA. So there will be a bias in terms of the intensity of roads that you have given by, like people are the ones putting. Are you all familiar with OpenStreetMap? Yes. Okay. So it's like a Wikipedia of streets. You go there and you draw the street that you see. Oh, there is no street here, and you just draw it. So it's crowdsourced in that way, but it's created, and all of these things. So that's why you will have more detail in places where people put more inputs than other ones. So after you have this, you have your representation of your street network. So you might have things that look quite horrible, but the roundabout is just one node. It's collapsed into one node, and all the different links of the street segments that intersect that one. Then you just run a thresholding procedure in which you're going to select a different distance that is going to be the threshold at which you're going to be creating your clusters, right? So for small thresholds, you will see initially just a few nodes. I don't know whether you can see, so here are the red stuff. So as I increase my threshold, I'm able to cluster more points together. So it's over the whole space. You don't have a seed from which it's going to expand. Okay, so doing that, then you create your tree. So this is very basic, I'm sure, for all of you. So you have all your nodes at initial distance that you say, if my threshold is bigger than 1, yes, sorry, smaller than 1, 1 is the minimum threshold, then I'm going to link them. So nobody's linked. And as I start to relax my threshold and allow for the message to pass above the initial 1, 2, then I start to see how I cluster the different nodes belonging to the same model cluster. Yes, and then you continue the procedure until all the nodes are clustered into one specific one. So these ones were done by Valentina, and that I think are very pedagogical. Okay, so then you construct your tree just using any this type of thresholding procedure. So what you have in the end is something that is telling you the intensity to which. So not only, of course, normally you cut the tree at some point, and then you say, here are my regions, and here are the cities belonging to my region. But here what we want to know is not only here are my regions, but what is the distance as well between the different type of nodes, and how, if you think about the structure of the system, how the measure is going to be changing as you go up and down the scale. And when you think about the whole thing, is that which scale is the relevant one, right? So at D equals 2, all of these were already one cluster, but all of these were separated. So what is that telling me about my urban system? Okay. So once you have that, then you put the population in each of the parent nodes. Okay, so you put the population such that, of course, everybody is accounted for. So the total population here is equal to the sum of all the children nodes. And what else? Okay, so as we traverse the tree, so this is important bit. So as we traverse the tree from top to bottom, we're losing uncertainty, okay? As we're traversing the tree. So how much we're losing? So before we saw that we have 1/2 because we were dividing the population in equal parts. But if we're not dividing the population in equal parts, then we will have a weighted sum of each of the children. Okay, so I have my initial entropy of the mother cluster, the parent cluster. And then I see how much entropy I had in each of my children cluster that is just weighted by the percentage of population that I have in each of those. Yes, so it's just a weighted sum of the entropy in there. And that's how I compute Jensen divergence. Okay, so overall I have this system here, so the model cluster, and then I have each of the children will have, you know, different weights of population, also of course different weights of groups, different weights of all of these ones. So the Jensen entropy will be given by this. This is exactly the same thing as before in a nicer type of node. So in order to be able then, so now that I have my Jensen divergence, so I'm traversing the tree and I'm looking at the entropy. So the entropy is telling me about the diversity of the groups that are in there. Okay, so that's we're talking about segregation. So we're interested into the diversity of the mix that we have and how it is subdividing into all these different clusters. So in order to be able to compare this cluster with this other one, we need to be able to normalize this measure. Okay, otherwise we wouldn't be able to be comparing things because of course you know that as the system grows, the entropy also will increase. So we compute the maximum of the Jensen divergence that we will get for each of those ones, considering that we have, you know, like this issue of the different population numbers, and we use that in order to be able to compare across the different across the tree. Okay, so of course, if all the children have the same type of groups, the same population and the same groups, I wouldn't have, my divergence will be 0. Yes, because I will have exactly the same thing. Okay, so Mateo is from Ecuador. Yes, and so the case study he used was from Ecuador because he knew very well the system and knew how to use the different data sets that were around. So when you look at Ecuador, it has all this range of mountains over here, and then it has the Amazonian in this bit. So all of this is very high in terms of forest, and then you have the main cities that you might have heard of: Quito, Guayaquil, over there. When you compute, when you see, okay, so what's going on in terms of socioeconomic characteristics of Ecuador, you see that the light, I don't know whether it's too bright here, but you might see some yellow patches. So the yellow patches indicate better off people, and the darker colors indicate less well-off people. And of course, the darker colors are concentrated in the more rural areas there is the Amazonian. And you can see in this one better. I think if you're all going to go to sleep, but might be better. Yes, you see, no. Anyway, so you see the green areas. I think maybe it's easier. The green areas are the ones that are better off. Okay, so you see how all the Amazonian bit, you know, it will be the bit that you know is struggling more, and the main Quito, Guayaquil, and Cuenca that you have over there are the very green bits that come into place. So one way to be able to study this system is to just characterize the different groups according to quartiles. So you just divide this index. So all of this is computed according to this index of life conditions that I think consider like education levels, whether, you know, like you have running water and all these different properties. Not entirely sure, don't remember very well what this index, but more or less it tells you, you know, like the socioeconomic, you know, how to divide the people into different socioeconomic groups according to this index. So Mateo decided to do this by quartiles, and then you can see more or less, you know, Q1 relates to the people that are less well off, and Q4 to the people that are better off. And so if you think about exposure and segregation, so the cities, the Q1s, will tend to segregate more, okay, and the Q4s will tend to be more to exclude themselves from different areas. If you think, apologies for this one, if you think with respect to accessibility, so apologies because these colors represent the bright ones represent in this one the better well-off, and in this one is the opposite. I've inverted the colors for this one. So the yellow ones are the Q ones, and the dark ones, no, it's the opposite. The yellow ones okay. Yeah, it's just that the colors were upside down. So the people that are better off have better access to schooling than the people that are less well off. And he also did this whole other study with respect to connectivity and infection, so COVID. Of course, everybody is very interested in this thing, and he computed the excess relative mortality during COVID. So what he did was to look at the behavior at the very local level over a window of 15 days, and to see how people, what was the excess death from the previous 4 years, I think. So he was doing this for 15 days windows, and then he was able to cluster according to the behavior of how people were, how there was excess death being presented into the system. So you cannot see very well the difference between the 2, 3, and 4 colors in this plot, but overall, what you can see is that there is some sort of, you will see that there is a similarity between the main city places, the connectivity of the system, as you will see, and how COVID was spreading. So here you will here are the days. So the big urban centers, one, will be presented early on, and the places that are more into the Amazonian, of course, will be later on, which is something that everybody has experienced. So if we think about how that relates to the connectivity of the system, and we have the index of life conditions over there. So darker colors or bright colors are better off than darker colors. And then you see by looking at the street network, how things are presented, you more or less can see that the connectivity of the system plays a big role into more or less saying what's going on with respect to the other ones. And that's, well, actually, I mean, you can see, well, that's what Mateo is trying to show. So as explained several times before for the ones that have seen this type of work, so you have this population processes, so you more or less can see where are these the different transitions, there are continuous transitions of the system, and how they are defining different entities that are having a significant effect into the system, like what would be a region and a sub-region according to the connectivity of the system. So this more or less doing this exercise, what you can do then is to have all your cities at the bottom and then see how they are connected into the different regions. And what are the regions represented with respect to the possibilities of encounters given by the street network, okay? So the regions are the possibilities of encounters, yes, the connectivity of the system, the possibilities of the probabilities, not the possibilities, the probabilities, the higher probability of meeting with people from those according just to the connectivity of the system. So there is, no, this is the threshold of, there is no population, it's the threshold of the connectivity. So if you think about it, yes. So this is a very, just to put things into context, this is Ecuador, has a high range of mountains, and you need to reach 12,000 meters in order to be able to connect the whole system. In the UK, you only need 5, but 5, the whole thing will be connected, okay? It wouldn't need to spread that much. So you see how, like just thinking in the UK here, everything will be connected, and you still have sub-connections and some regions that are really disconnected from other parts of the system. So this is why, like, the road network plays a big role, because you don't have
a railway that is connecting all of these systems, as you will expect in Europe, for example, in order to be able to reconstruct this in a way that is more sensible to sort of things you will expect in Europe. Okay, so doing this exercise, then you compute the Jensen-Shannon divergence through the tree. So of course you start with your entropy, so that's why there are no colors here, and then you see the divergence at each of the levels of the tree. So because it's normalized, then you're able to compare the different colors, okay? If it wasn't normalized, you wouldn't be able to do that.
The last one, those from Ecuador. What are the leaves? What are the patterns?
So the bottom are the cities.
Yes, but in Ecuador there is no city there.
Sorry?
The last one, the direction. We don't know.
No, there are no names for all of them, just to identify where are like the main cities. But for all of this,
There are
you cannot,
cities that connect through Ecuador, but they don't connect to other cities.
like for example, if from Santo Domingo, I wanted to go to Quito, I have to go up the tree and I connect until over there.
I guess that if you go to Quito, you go to where, no?
If you go to Quito, you're better connected to these other ones. So still, in order to go to Guayaquil, you still need to go up. Yes. Yeah. Cuenca, yeah, that's it. You've been to Cuenca?
Ah, I haven't been to Ecuador. But now I want to go, now that I know so much about it.
Isn't it like Guayaquil is better connected than because Guayaquil is like 5 steps, 6, yeah, like 5 steps. But Quito has more like 7 steps, no? Yeah, I agree. Guayaquil is better connected to all of these other cities than Quito, definitely. Yeah. Because in order to get here, so you see how many steps you have to go up the tree here in order to connect. Well, here, you have to go up until there. Single 6. And this is only 5 to connect to all of these other ones because they belong to the same region.
And actually, Guayaquil, it's a city that does very, very well. So the idea, what Mateo really wanted to show is, many times you might be looking at a city and might say, oh, there is a lot of segregation going on, right? Or maybe there isn't much segregation. But then what happens at the next scale with respect to who is commuting to the city or who is part of this regional level? And so by looking at how, as you cross the tree, you change the state of the divergence, then you can really see when you have the maximum. So this is what Mateo proposed, right? So you have the normalized Jensen-Shannon divergence, and then you look at each of the cities that start here, and you see what's going on with the trajectory of the cities as you traverse the tree. So as you go up the tree, not all of them go down or go up, right? So they are changing their status. So when I'm looking at that, when do I get the maximum of this Jensen divergence? So what it's telling me is that maybe here I didn't look as segregated, but once I go up the scale, I'm integrating all the agricultural settlements in which I create a lot of segregation in my space, okay? Or maybe I was really segregated at this level, but then once I'm incorporated into the larger system, the problem is more at the local level than at the regional level, okay? So more or less the idea of being able to understand that. And so this is what happens. So for example, if you look at Quito, this region, given that you've been there, or you've been to Cuenca, right? Where's Cuenca? You've been to Quito. Okay, so maybe Quito really, doesn't show such a big problem until you get into this mega region when you incorporate all these other different centers, okay, which most certainly they relate to agricultural levels. But for example, if you go to Guayaquil, it's very segregated. So in this one, you will have it, at the more local level instead of going up the tree. And so with this, what Matteo wanted to say is that if you're thinking about the social problem, it's not about this city or this other one or this region. It's really to understand at which level you're going to be thinking about intervention. Where is it that you have, like where are the main problems? You don't have the problems always at the city level. Sometimes you do, but sometimes the problems are incorporated at a higher level. So you don't have a unique scale in order to be looking at segregation. You need to understand the whole system in order to see, well, maybe once I change this, I won't have as many problems into this other one, but sometimes it's the opposite. It is only at the regional level that you encounter these sort of things. So these are more or less, like by selecting the clusters of maximum divergence, then you're able to say, okay, where in my space I should focus my intervention with respect of where am I having this segregation? Is it due to is the a lack of catchment with respect to labor flows, or what's going on in my system? Okay, so this is it. So to conclude, overall, all of what we're trying to do at CASA, is to understand urban systems in general from the perspective of complexity science. That means that one scale is never enough. You need to understand the relationship between the different scales. Segregation is one of those, but you can think about any other kind of measure. This was only one measure, segregation, but it could be anything else. That you measure how it changes across the space and how the scale at which the phenomenon is happening is affecting all the other ones. So there is no unique scale at which the process is going to be important. Nevertheless, if you want to do an intervention, then you need to understand which is the scale that will kind of have the maximum effect for all the other ones that will propagate more into the system. And with this type of thing, so it's not only about segregation at one level, but it's also taking into account the connectivity of the system. So thinking about the measure across the space, across the different scales, takes into account as well how the relationship between the different systems are telling you about the connectivity of the system. And this is Mateo's work. Well, one chapter 5 of his thing that he just finished. Thank you.